times R would be equal to E naught. If you assume R to be something, you have to assume that R is equal to R naught e to the minus I omega t. And then you call this R naught. R naught will be given. If you substitute R to be that in there, a time harmonic solution, then what you find for R naught, and then you find your P, your mu, from this equation will be given by E over minus ME omega squared minus I omega ME gamma times E naught. Okay. So this gives you the relationship between P and E and give you chi. Okay. So I can add an n to here, put an n here, and this will be my P. And then this would be my epsilon naught chi E naught. Okay, kind of E naught. E naught and E are the same. Okay, you know what I mean by that. And then so when you have that, then you can have this epsilon part, just this part over here, which is 1 plus chi. Okay, if you add 1 plus chi, then you have this, that the group model for this is just 1 minus omega p squared over omega squared plus gamma I gamma omega. I think that's correct. Okay. If you take this out, put omega squared outside, you take that in, and then you lump those things together and put an epsilon naught in there and call this omega p. And omega p is something that you might have learned before. Omega p is called the plasma resonance frequency. It's going to be something like n e squared over mass effective times epsilon. If we work this out correctly, lump this together, and divide it by epsilon naught, you get omega p to be that number over there. Okay, this is called the plasma frequency, and you probably have seen this formula before. This is collisionless plasma. This is usually called collisionless. This should be a less there, or cold plasma. You probably have seen this formula in your undergraduate course, right? How many of you have not seen this formula before? So I think all of you have seen this in your undergraduate course. We always talk about this, cold plasma, collisionless plasma. And then epsilon can be negative, that is, if omega falls below the plasma frequency, it becomes negative. And when epsilon becomes negative, what happens? What happens when epsilon becomes negative? What is the first thing that comes to your mind? Detail what comes to your mind when epsilon becomes negative.
Omega p squared omega squared.
Yeah, greater than 1, so it becomes negative. What kind of physics comes about? The first thing that comes to your mind. Epsilon becomes negative. What?
Omega p squared.
Yeah, but what? That's mathematics, right? What physics would come about?
K becomes lossy.
What?
K becomes lossy.
Yes, K becomes pure imaginary. K becomes pure imaginary because K is equal to omega mu epsilon. If epsilon becomes negative, K becomes pure imaginary. And wave cannot propagate. There's no more plane wave solution. And what is the natural phenomenon that you often see that affects your everyday life? Ionosphere, very good. Ionosphere, okay? Marconi was very lucky. His experiment would not have been successful if there was no ionosphere. Marconi was able to send the first radio signal. Was it from England to Newfoundland or Newfoundland to England? I forgot which way it went. Okay, and the Earth's surface was curved. He didn't know that, and he sent his radio signal, and there was no ionosphere that bounced back his radio signal. They would not have received this radio signal at the other end of his experiment. So he was lucky. He didn't know about that. He just sent his radio signal, and how people heard him across the Atlantic Ocean. And because of the ionosphere. At that time, radio signals were very low in frequency. Because they were very low, most of the time epsilon was negative for the ionosphere. And nothing can propagate through the ionosphere. So when you have to talk to the satellite out there, you have to work with frequencies that are above the plasma frequency of the ionosphere, which is probably in the order of gigahertz range. That's why all the satellites talk to each other at microwave frequencies. They don't talk to each other, and they don't talk to the ground station using radio frequencies or megahertz frequencies. I don't know, I don't remember what the plasma frequency is now of the ionosphere. Does anybody remember? It does change with the day, that's right. Depending on how hot and how cold the plasma becomes, how much the sunlight has on it, it actually changes the plasma frequency. It changes with the density. The electron becomes of different density depending on how hot the ionosphere is. Okay, so the plasma frequency does move around depending on the time of day and so on. Okay, but this is essentially a very simple Drude model. So it's also because of this very simple Drude model that contributes to negative epsilon. And it's because of this thing that we have negative epsilon at optical frequencies. In microwave frequencies, this term would dominate because this term is very small at microwave frequencies. But when you go to optical frequencies, this term becomes substantial because omega is very high. So when you go to high enough optical frequencies, this term becomes important. This term becomes less important. Microwave, this is very important. Lossy. Metal is lossy. Metal is never negative epsilon. Metal always has a skin effect, but when you go to optics, gold particles are quite different. Okay, so my students always ask me, what do professors ask you in the qualifying exam? So once I asked a student, he presented this formula. I asked him, which term contributes to the negative epsilon in the gold nanoparticle? He didn't know, he couldn't answer. So if I ask you the same question, which term contributes to the negative epsilon? Which term? The inertial term, right? It's very obvious from the math. It's the inertial term that contributes to the negative epsilon. It's this term. This term has to dominate. If that term doesn't dominate, you don't have negative epsilon. That's why you observe negative epsilon at optical frequency in gold particles. And you can think of gold as consisting of a sea of electrons. That's what a simple picture of a conductor is, a sea of electrons. So this sea of electrons at microwave frequencies would just have a very simple lossy picture, but when you go to optical frequencies, the inertial term of the electron becomes important, and then you start to see negative epsilon. Okay? So we know something about this, and then so there is another model which is slightly different from the Drude Sommerfeld model, which has to take into account atomic transition. In the fact that the Drude model assumes that the electron is bound, is actually not bound to the core, the electron is actually, you have a positive charge there. The electron is actually free to move about very freely. And there's no bound. There's no spring constant that attaches the electron to the atom. Okay, the only thing that slows down the electron is this term here. But what happens if the electron is actually somewhat bound to the core of the atom? You can model that classically as a spring. So there are some models that put in this spring constant to account for the fact that the electron is not that freely moving in many cases. And in that case, the model that you would have would be something like this. This is like a spring constant term. And this is still a classical picture. And this is like Hooke's law, right? Spring constant, Hooke's law, which is force is equal to some constant times x. This is Hooke's law. The spring constant times x. So larger you pull the spring, the larger you have to exert the force. This is Hooke's law. And this is essentially the term. The larger the displacement, the larger is this force. And then if you solve this equation, you get a somewhat different epsilon, somewhat different from that. So the atomic model, with the fact that the thing now is bound to the atom, this epsilon will give you some other things. You get somewhat different omega p squared. Okay, and then you will have this resonance term, omega naught square minus omega square. Plus this I gamma omega, plus this loss term. So that's what I have in my term. And this is the collision term, and this is the spring constant term. So if there's no collision, when you hit the resonance frequency of the spring, you get infinity. Okay, there's no collision. But the collision kind of attenuate this effect of resonances. Otherwise, you will have huge resonance. Okay, and according to my notes here, omega p is very similar to what we had before, with some kind of density times E squared times the mass in that model times epsilon naught. Okay. Omega naught is just a spring resonance frequency. Hooke's law. Hooke's law, the resonance frequency of a mass attached to a spring is given by this formula. Square, usually you might see in some textbook that says the resonance frequency of the spring. This is just that. Okay. Okay, any questions so far on this surface plasmonic effect? And why we get negative epsilon for gold and not for microwave? And why we get negative epsilon for the ionosphere very easily? Because the ionosphere is very rarefied. It's very rarefied, and hence it's very easy to have plasma. And when the ionosphere is very rarefied, this electron just move about freely, not tied to the core. And there's an ionospheric plasma out there very easily formed. And when that happens, then you get this negative epsilon very easily. So two places we observe negative epsilon very naturally, the ionosphere and gold nanoparticles and silver nanoparticles. Silver, good conductors. Gold and silver are very good conductors. Okay, they have lots of electrons in them, freely moving about. And the optical frequencies, those electrons contribute to negative epsilon. Okay, let's take a 5 minute break and come back.